Hello everybody. So let us now continue our discussion from where we left in the last lecture. So in the last lecture we were looking at the concept of phase transfer catalyst, where we were looking to investigate the nucleophilic substitution reaction in a halide substituted compound when we treated with this potassium salt of A minus. In this case my A is my acetate ion and X is my chloride, is my chloro atom. In the presence of ground ether, we would like to see and investigate the replacement of X by the A species and investigate the reaction kinetics of the process. Now what has been observed is that when this reaction was done in the absence of ground ether, then the reaction half life was 685 hours. When we added 18 ground 6, it increased to 3.5. I mean to say the reaction time decreased to 3.5 hours drastically, and in the presence of dibenzo 18 ground 6 and dicyclohexyl ground 6, the reaction times were 9.5 hours and 1.5 hours respectively. That means there is a special role of the ground ether in these processes, and this enhancement in the rates of the reaction via metal ion complexation with the macrocycle enhancement in the rates of the reaction via metal ion complexation with the macrocycle modifies the conformation of the macrocycle with subsequent implications in reactivity. So we referred to this enhancement in the rate of the reaction occurs in the sense that there is a catalyst which actually catalyzes this process, and the catalyst which is involved is the complexation of the metal ion with the macrocycle, that is the 18 ground 6, which effectively enhances the rate of the reaction. Now how does this take place? So to start with, let us consider the reaction vessel in the following way. We have got, say, this is the aqueous phase and this is the chloroform phase. So this is the organic solvent, and now what I am doing, I have taken the corresponding potassium, I have taken the corresponding potassium acetate, and it is in aqueous phase. You see that the cation and the anion are solvated, however there exist ion pairing. Now what the macrocycle does is that the macrocycle encapsulates the potassium cation and forms the crown ether complex, and the crown ether complex now comes into the organic phase. It comes into the organic phase, and now the acetate ion is free to perform the chemical reaction. So initially potassium acetate was the potassium and the acetate ion are tightly held because of the electrostatic interactions, and these electrostatic interactions are also favorable in the polar phase. However, when we add the crown ether sequesters or captures the potassium cation and frees the acetate ion. Now this particular crown ether complex has a different conformation, because we know that the crown ether complex, the crown ether when it is uncomplexed has got a different conformation compared to the conformation it adopts when the oxygen atoms now point towards the interior where the potassium ion binding takes place. So, this particular conformation now is where the exterior part is more non-polar, is more favorable in the organic phase, and therefore, the potassium ion is removed from the vicinity of the acetate. The acetate is now freed up, and now the acetate as a nucleophile can attack the carbon electrophilic center and form the resulting product. Now, once the product formation has taken place, it is to be realized that the inorganic byproduct KCl is also formed. The inorganic byproduct KCl is also formed. So, what happens is that now you see you have got the crown ether plus KCl plus my organic product here in the reaction vessel, and but the inorganic salt is not stable in the organic phase or in the organic solvent, and therefore, now it comes back to the aqueous phase. It now comes back to the aqueous phase, the inorganic product, and the crown ether is also not stable in the organic phase, because now it does not have the potassium cation and it adopts a more polar conformation. The polar conformation is more stabilized in the polar solvent, and therefore, the crown ether, the uncomplex crown ether, now goes back to the aqueous phase. Again, it takes up the starting material, that is, it takes up the nucleophile, that is the potassium acetate, again brings the organic nucleophile into the organic phase, and the chemical reaction proceeds. So, this transfer of the reactants from the aqueous phase to the organic phase in which the chemical reaction takes place is brought about by the potassium cation, and this leads to tremendous enhancements in the rates of the reaction, which is facilitated by the cation and complexation. So, and hence this is reflected in the extremely short reaction half life for the 18 crown 6 and even lowered reaction times for the dicyclohexyl crown ether complex as well. So, this is a very interesting application of phase transfer catalyst, which is mediated by the crown ether complexes, and in this regard the application of crown ethers in the presence of potassium ions is very important, and it has also been realized that other cations do not bind very efficiently with crown ether. The binding is most efficient with the potassium ion. So, keeping the fact in mind that reaction rates are tremendously enhanced in the presence of the potassium cation, it has also been realized that to perform organic chemical transformations, the potassium ion has been utilized to create a template that shall facilitate processes that govern intramolecular ring products, intramolecular ring products, that is we can say, or we can say intramolecular cyclic products. So, if we want to have a chemical reaction, doing about a chemical reaction where there is a competition between an intermolecular process and an intramolecular process, then the potassium ion has been utilized to create a template that facilitates processes that govern the formation of the intramolecular cyclic product in preference to the intermolecular products. Let us take a particular example. For example, let us take this particular acyclic component and the corresponding dichloro compound, and we treat it in the presence of KOH, potassium hydroxide. Now, what potassium hydroxide does is it is acting as a base. It is acting as a base, and what has been observed is that so you have 1, 2, okay. So, we have these two reactant partners where we have the dichloro compound and we have the dihydroxylated compound, and we have the corresponding potassium cation which kind of forms a template, which kind of creates a template, and then what happens is that the nucleophilic reaction now proceeds in a very enhanced fashion, because now the base generates the O minus, it attacks the electrophilic carbon, again it attacks the electrophilic carbon, chloride goes out, and minus 2 HCl equivalent molecules are removed, and we have now the final product. So, now we see we have got 12, 13, 14, 15, we have got the 18 crown 6. So, we have got the cyclic product, and if we do not add KOH, but we add a simple base, that is triethylamine, then a polymer is formed, because statistically in the presence of triethylamine we generate the O minus, it hits the electrophilic center, it forms a carbon carbon bond, and we get so now we get this linear polymer, we get a polymer. So, essentially it leads to a reaction where I have got an intermolecular process which is happening, and I get a long chain polymer, and the possibility of a cyclic reaction to take place is very remote. So, this process is very difficult, getting the cyclic product is very difficult. However, in the presence of the potassium ion, it creates the template, the necessary template, we can say the necessary playground, when the reacting partners can come very close to each other. These are the reacting partners, they can come very close to each other, and the groups, the functional groups which are supposed to react with each other are also in the close proximity. The SN2 reaction can take place, and the cyclic product formation happens in a very facile way. The rates of the reaction are tremendously enhanced, and the entire process is catalyzed via this template formation, and this is referred to as the primary template effect. This is referred to as the primary template effect, and it is as if this the close proximity of the reactants creates an intermediate which that facilitates the formation of the cyclic product, and this is referred to as the primary template effect. And it has also been observed that this effect can be templated can be also be templated by other cations like the alkali metals, like sodium or the alkaline earths, lanthanides, etc. So, different kind of metal cations can actually catalyze this process, and this is referred to as a primary template effect or a kinetic template effect. This is referred to as the kinetic template effect, because here the processes that govern formation of the product are of a kinetic nature. Now, along the same lines, we have also got the formation of products that are governed by thermodynamics. That are governed by thermodynamics. So, we see that in kinetic effect, template effect, the actual formation of the complex with a given arrangement of ligands around the metal center takes place. But in a thermodynamic template effect, it depends on the ability of a cation to pick up a ligand complementary to it from a equilibrating mixture of products such that the most favored product is also the thermodynamically stable one. So, we looked at the kinetic template effect, and we now look at a thermodynamic template effect, which depends on the ability of a cation to pick up a specific ligand that is complementary to it from a mixture of products which are in equilibrium with each other, such that the final obtained product is also the thermodynamically most stable one. And let us look at one particular example where the formation of or the demonstration of the thermodynamic template effect has been relevant. For example, it has been observed that, let us take M, a tris ethylene diamine dicationic complex treated with acetone gives you this particular complex. And So, to start with, we have got the ethylene-diamine ligand that is complexed with the metal ion. So, for the ligand to complex with the metal ion, it forms an initial complex, but then we want first the ligand En to react with acetone, and therefore decomplexation has to take place. Decomplexation has to take place. In other words, the metal ligand bond has to break, and this is only possible if these are kinetically labile bonds. And inert complexes, kinetically inert complexes, do not contain labile bonds, and therefore those kind of complexes, for example, if you were to consider cobalt En3 3 plus, okay, in this particular case the cobalt is a 3 plus cation, the cobalt nitrogen bonds are kinetically inert and therefore they are not labile, and because they are not labile, it is very difficult to undergo decomplexation, and hence reaction of the ethylene diamine with acetone does not take place. And in this case of thermodynamically template effect, we do not need, in some cases, the presence of the metal ion to template this particular process. So, if for example, the final product does not necessarily need a metal ion to template this process, does not need a metal ion to template this particular process. Now, let us look at how this particular complex is formed. So, we have got the ethylene diamine ligand, which is NH2, and we have got acetone. So, acetone will react with the aniline with the amine group to form the imine. Okay, so it forms this particular ligand first. So, the reaction of ethylene diamine with two equivalents of acetone will give this particular ligand, which is actually in equilibrium with the starting materials. Now, another equivalent of this ligand okay, in the presence will now undergo cyclization in the way that we will have now a CH2 minus, and here we will have a CH2 minus, and this process followed by the proton. So, the nucleophilic attack, because this is base catalyzed process, where you have the CH2 minus which attacks the electrophilic sign of C double bond N, and followed by the proton transfer, will give you the desired ligand. NH And so now we also have the equilibrium of this final ligand. This is the intermediate ligand, and these are the starting ligands. So now the thermodynamic template effect is such that you still have the metal ion which is present in solution, and now the metal ion can have an affinity for either this ligand, or it can have an affinity for the solvent. It can be solvated by acetone molecules. It forms an initial complex with the ethylene diamine, and now it can get stabilized further via both Chillet effect and macrocyclic effect, and both these effects stabilize the metal ion in this particular template or the final structure of the ligand, which is the thermodynamically most stable structure. That particular ligand is now picked up by the metal ion to form this particular complex. And we have also realized that in the formation of this complex, it is not necessary for the metal ion to be present. As long as there is an equilibrium between the starting material and the different ligands which are being formed, once in this equilibrium or in this equilibrating mixture of ligands, the metal ion will pick up the corresponding most stable ligand and form the thermodynamically stable product. So this is a very interesting example or an expression of the thermodynamic template effect. And keeping this thing is in mind, people have further explored this thermodynamic template effect to make different kind of metal macrocycles, either containing the metal or without the metal. Depending upon the size of the metal ion, we can now achieve macrocycles of larger sizes as well. For example, we can consider a reaction where we can have this particular ligand being treated with this diamine, which is bridged by two etheric oxygens, and now we are going to take two different type of metal cations. We are going to take two differently sized metal cations. In one case, we are going to take manganese, iron 2 or magnesium. In the other case, we are going to take barium 2 plus or lead 2 plus. In the first case, we are going to take both the ligands in 1:1 stoichiometry. That means one part of this and one part of this. In the second one, we are going to take in 2:2 stoichiometry. And it will be interesting to see what is the final product obtained. In the first case, you will have the reaction of the amine group with the keto functionality to form this particular product, where now my metal ion sits and interacts with the nitrogens as well as the oxygens. And in the second case, it is going to form a much larger sized macrocycle. This is a much larger sized macrocycle, in which my large cation like barium 2 plus or lead 2 plus is going to sit, whereas here the relatively smaller size cation is going to occupy. So the size of the macrocycle depends upon the size of the cation which is templating this macrocyclic effect. So, this again demonstrates the operation of the thermodynamic template effect, and the size of the template which is being formed, the size of the ligand which is being formed again depends upon the size of the metal cation which templates the formation of these kind of final ligands. So, and the next part here is, in this particular process, is whether we can effectively remove the metal cation from the macrocycle and free it, and this can be done by adding ligands with which the metal ion complexes strongly. For example, we can take KCl, and the cyanide ion complexes with the metal cations which are the divalent cations very strongly to form this kind of species. So, if you have nickel for example, then it will form NiCN4 2 minus, or if you have lead, sorry, if you have nickel, it will form the NiCN4 2 minus, it is very specific for that of nickel, or if you have palladium or platinum, it will form the corresponding tetracyano palladate or platinate complexes, and therefore the metal ion can be removed from the macrocycle and the ligand can be obtained. So, all these results demonstrate to us the relevance of template effect, both kinetic as well as thermodynamic, in the formation of larger size macrocycles, and with this we have got a very we have got a complete overview of this class of ligands, the covalents, the podents, the crown ethers, cryptends, and we have also looked at spherents. In the next lecture now, we will now go on to the other classes of molecules which exhibit host gas complexation behavior. For example, we look at calixarenes, we look at cyclodextrins, and so on and so forth. Thank you.